integral methods for solving these boundary layer equations. So those integral methods were developed quite a few decades ago, and mainly because they had no computational power at the time. So they had to find ways to try to understand what's happening without being able to do the types of numerical simulations that we are able to do today. And they were able to look at and see what would happen, at least from a more qualitative standpoint and quantitative standpoint. Okay, so there was these one equation methods, and I think we started introducing two equation methods, so dissipation methods, for looking at what happens in these boundary layers or trying to get approximate solutions to them. So I think we stopped where we talked about dissipation methods. Bless you. Okay, let me just get our equation again. So we got that. So we got the integral, or the one common integral momentum equations by multiplying the continuity equation by u minus ue, and then adding it to the momentum equation. And then we introduced a kinetic energy type equation where we, instead of multiplying the continuity by u minus ue, we multiplied it by u squared minus ue squared. And then added it to the continuity equation times ue and simplified it a bit. Okay, so I think that's the last thing we wrote. So we had equations that looked like this guy. So I think we ended with the theta. So this was the one common integral momentum equation. 2 plus h theta ue due dx. Okay, and CF was our skin friction coefficient. Theta is our momentum thickness. And that du d theta term, it comes out of your pressure gradient, or your pressure profile. And so this is what we got. So this was the one common integral equation. And then we found the kinetic equation, which was dh dx 1 over dh star dh. To CD, and this CD here, it's not drag coefficient, but dissipation coefficient, minus CF over 2. Alright, so I think that's where we stopped. And h, of course, is our shape parameter, and it's the displacement thickness of the momentum thickness. H star was our kinetic energy thickness divided by the momentum thickness, so we know what those terms are. So this guy here, we just put them up. So h is our shape parameter, defined by displacement thickness over momentum thickness. H star, this was our kinetic energy shape factor. And that is theta star divided by theta. And that's momentum thickness. It's theta. Theta star is our kinetic energy thickness. All right, and we have, I believe we have the definition for those in your notes, so I'll leave them out here. All right, so with these dissipation methods, so it looks at solving these two equations. So it's based on the hypothesis that the Reynolds number defined on theta, so defined on our length scale as the momentum thickness. ICF is a function of h only. The Reynolds number based on theta, so that these two quantities, so the displacement, the dissipation coefficient, and the skin friction coefficient, are only functions of h. Okay, where the Reynolds number based on theta, u e theta on nu. And this is a bit different, so this definition is a bit different than what we would have seen for the one equation systems, where we defined our Reynolds number, or we defined our quantities, Re theta, Cf was a function of this lambda parameter. Okay, so this was the one equation method, and in particular that's what was Thwaite's method in particular. Alright, so this guy here again is dissipation coefficient and not drag coefficient. Okay, and then we also have h star, which is also a function of h. So all these guys are functions of your shape parameter. Okay, so with these methods, what we actually have, we have a system of two simultaneous ODEs to solve. All right, so we have two simultaneous ODEs that we need to deal with for theta and h. And we could do that once we know what our velocity field looks like, or what our edge velocity field looks like, which can be integrated given u e. So once we know our edge profile, we could figure out, well, we could solve these equations simultaneously. Now, that's not as straightforward. It's usually something that is done numerically. There's also been charts and tables and stuff that are developed to help you solve these two equations simultaneously, and it takes a while to actually step through it. It's a fairly intensive process, especially if you had to do it by hand and not by computer. And one of the methods that was a bit simpler, I think it's by a guy named Head in the 1930s, I believe. He has a chart and table that helps you go through this, but it takes about 15 to 20 minutes to actually go through the solution at one step. And then depending on how many of these steps you have to take, you could imagine how long it would take you to get an approximation doing it by hand. But at the time, it was a really good approximation. He gets it to within 1 to 2% of what you would get if you used a numerical computational type approach. So the method itself for the time was pretty good to get a decent approximation. Bearing in mind that they didn't have access to these computers that we have now, so this is the sort of stuff that they would have had to resort to. All right, but I'm not going to go through the actual solution method. But I want to talk about some of the results and some of the stuff you could observe by looking at the results that you get by looking at some of these methods. All right, so if we were to plot some of these parameters that we're interested in, so this Reynolds number times skin friction coefficient and dissipation coefficient. So if we were to plot these based on those solutions, so I'm plotting them against our parameter h, we would get for the Reynolds number times the skin friction coefficient would look something like this guy. And this would be Cf by Reynolds number based on theta over 2. And if we were to plot the other parameter, it would look like this guy. Just a second, let me redraw that. So it looks like this. Okay, and this is the CD R theta over H star. And the interesting parts here, so this, where these two values turn out to be the same, is actually the point where you would be looking at, so this would be 2.6, and this is the case where you have a Blasius solution for boundary layer. So this would be for the case where you have flow over a flat plate, constant uniform flow over a flat plate, and you could solve the boundary condition, the boundary layer equations for that case. So this is Blasius. Solution, so this is flow over a flat plate. And this value here, where with skin friction goes to 0, so is no longer any shear stresses on the surface. So at that point is where we have separation. So if you'd have flow separation at that point where the shear stress goes to 0. And that value turns out to be 4. Okay, so right here we'd have separation. So the shear stress on the surface is 0. And this side of it, so these values on this side are usually represented for cases where the velocity is increasing, or the velocity at the edge is increasing. On this side of it would be profiles where the velocity is at the edge is decreasing. All right, one of the things we should note by looking at the simultaneous equations that we have to solve, so we'd note that h minus 1, so for this equation, so we could see in here, this guy, so that h minus 1 multiplies our pressure term again. So just in case we forgot, so remember we got this term here by applying Bernoulli's equation for the conditions that we're looking at, and we could relate the pressure gradient to this particular term. So it's relating, so it's this times our pressure gradient term. So this H, I would say it drives itself. When I say drives itself, I simply mean that if H is large, then it's telling us that the boundary layer is sensitive to pressure gradients. So if H is small, then it's not as sensitive to pressure gradients. All right, so the actual magnitude of H kind of gives us how important that pressure gradient is. Question?
I'm having a kind of trouble having some sort of physical feeling for H.
H.
And I see it's like the ratio of the displacement thickness over the momentum thickness, but
yeah.
what is that?
how could I best explain that? See, it's physically. I'll have to think about that a bit more and get back to you to kind of get a real physical grasp of it, because it kind of represents it's a representation of the geometry that you're looking at. So that's why it takes different values for like a flat plate, or different values for different orientations. So say flow over a wedge at different angles, it would assume different values. So that's why they call it a shape parameter, because it has to do with the usually has to do with the geometry of what you're looking at, what the flow is going over. But I need to think about getting a more concrete physical example for you. That's as
maybe like large H, you can think of like flow over a step almost, you know, like kind of expanding the flow so that you have that adverse
pressure gradient. Yeah. Yeah, that
slows the flow down.
Yep, that would be a better way to look at it. Yeah, so so I guess you could look at it in terms of maybe like the orientation, because it has to do with that, the shape of the object that you have flow over. Right. So that's the best I could probably do right now, without thinking about it a bit more. So it has to do with the shape of the object that you have flowing over. All right. Okay, so that means, so if H is large, the boundary layer is more sensitive. Boundary layer is more sensitive to pressure gradient changes. Okay, so looking at these two equations, so the d theta, dx equation, and equal to all that other stuff, it governs the evolution of the boundary layer, of the boundary layer thickness. Evolution of the boundary layer thickness scale. Boundary layer thickness scale. And this dH equation, dx, all that other stuff governs the profile shape, the shape over which the flow is flowing. Governs evolution of profile shape. Okay, so in contrasting the one equation methods, integral methods, as opposed to these two equation integral or dispersion methods, so in contrasting between those one and two equation methods. So with the one equation methods, we looked at the Reynolds number based on theta times disconnection coefficient as a function of theta UE and our pressure gradient term. H was also a function of those guys. Theta UE. So it's in essence, so these guys depend, or H especially, is what we could term like a kinetic term. It's based on the shape that you're looking at, not really on the physics of the flow and stuff that's around it. Okay, so this is a kinematic, we want to say a kinematic quantity. and it's as a function of these dynamic quantities. Dynamic quantities. Whereas with the two equation method, so this is the one equation method, but with two equation methods, we have Reynolds number based on theta for the friction. That was a function of h. Re theta, the dissipation coefficient, it's also a function of h. And then we have h star, it's also a function of h. So here we're relating our kinematic quantities as functions of kinematic quantities. Okay, so they tend to give better results. Okay, they tend to be a bit more accurate than the one equation type of approximations. Okay, so let's see if we could say a little more about the behavior of the boundary layer, looking at some of these two equation methods, see if we could get a little bit more information as to how these boundary layers behave. Okay, so we'll talk about boundary layer behavior. And we're going to use the example of flow over a flat plate. Boundary layer behavior, sorry. Okay, now example, we're going to use flow over a flat plate, so our goal is to just gain some insight into how various terms in our two equation method drive boundary layer behavior. So how various terms this two equation method drive boundary layer behavior. Okay, and I will just correct my British spelling of behavior up here. Behavior. Okay, so Trinidad was a British colony, so we still put all those U's and stuff in there, as opposed to up here. So I'm trying to get into the habit of leaving those U's out. So just excuse me if you see it pop up every now and then. All right, so behavior. Okay, so for this problem, we're going to look at flat plates. So we have our flat plate. We're going to have flow over it. But now we're going to look at a case where we're going to vary the edge boundary layer. And we're going to achieve varying the edge boundary layer by doing it in a channel where we're going to change the width of the channel. So we could change what the velocity does. All right, so it's inside of this channel where the height of the channel changes. All right, we want to look at what's happening with the boundary layer as it develops on this plate at the bottom. So you expect it to develop something like that. So right here, it's where our velocity is changing, our profile is going to change, our pressure profile is going to change. We call this point here x1, call this point x2. So we expect the boundary layer to develop in this region. Typically our boundary layers develop, and then there's going to be some type of change in here. So it's going to get bigger in here as the velocity changes. And then I'm not sure what's happening here. So at this point, so there's some transition to some new velocity. And in this case, we're just going to use, say, an example where we want to put a number to it so we could kind of quantify some of it. So say it's changing by 10%. Okay, so if it's a value of 1 here, it's 0.9 here. Question?
So is it stabilized before it hit X1? Or
If it's
steadily growing till it hit X1?
it's that we could look at it from the point of steadily growing. So it's developing. Okay, for this case, we're kind of just looking at the behavior of what's going to happen to it as it goes through this type of change. Okay, and in particular, we're going to look at, so in this case, we're going to say about a 10% decrease in velocity. So a sudden decrease, and about 10%, we'd say, just so that we have some numbers to work with, in UE. So in our edge velocity on, and this is for the flat plate. Okay, so the two things we're going to look at is, okay, so will this flow separate or not? So is the flow going to detach and are we going to have some recirculation or not? And how much would our boundary layer thickness kind of increase? Those are the two things we're going to look at. So we're going to look at, will boundary layers separate? And the second thing we want to look at is, what is the increase in theta? Okay, so in these, our length scale that we use to look at our profile is the momentum thickness. So we're going to look at the momentum thickness. All right, so to get some insight into this, we're going to look at those two equations. So let's change the form a little bit so that it clears it up a little bit. So instead of using the equations as we wrote them here, so we're going to look at these two equations. I'm going to write them in logarithmic form, just to make it a little simpler for us to see what's happening. Okay, so in logarithmic form, I'm simply doing something like this. So I know that d of log theta is 1 over theta d theta. So I'm going to be making substitutions like this into those equations for terms of du and d theta and dh and that sort of stuff, or dh star. So these are the type of substitutions we're going to be making. So let me rewrite those two equations in log form. Okay, so let's use the log form. Logarithmic form of that von Karman integral momentum equation and that kinetic energy equation. Alright, so writing it over in this form, so using this guy for theta, and I'd use a similar thing for du, similar thing for dh star. I could rewrite it like this instead. So dx d theta times ln theta equal to 1 over theta cf over 2 minus 2 plus h d dx d ln u e. Okay, so that's the momentum equation, and the kinetic energy equation I could rewrite as d dx ln h star equal to 1 over theta times 2 CD over H star CF over 2 plus H minus 1 D dx ln UE. Okay, so that's rewriting them in logarithmic form. Okay, so to check for separation, we're going to look at this equation. And the reason we're going to look at this equation is because at separation, so I'll go back for a quick second. So when we had separation, we knew what the H value would look like, where this thing separates. So that H value has to be 4. Okay, so we're going to look at this equation since this is what governs H to figure out what's happening with separation. Alright, so to check for separation, we use the kinetic energy equation, sometimes called the kinetic energy shape parameter equation, same thing, so that's this guy. Okay, so let's integrate this guy between x1 and x2. So we're going to integrate between x1 and x2. Okay, so we're going to integrate between x1 and x2 of this guy. So that's this guy. So I'll just write that so I don't have to keep writing it over. There's that thing in brackets, dx. Alright, so all that stuff goes into here. Okay, so it's going to be a bit complicated to do it, but we're going to just assume that things are going to be constant over that little integral or that little region, so that we could assume that a lot of these terms are constant. And I could, in that case, I'm going to assume that these things are constant and that I could use the average value of theta between 1 and 2 for these terms, just so that I could get an average interpretation, an average feel for what's happening. Okay, it's not going to be exact, but it's going to be a decent approximation over a small interval. Okay, so that's what we're going to do. Okay, so I'm going to assume that all these values here are going to be constant over that particular interval, and I could use the average values here and here. So theta 1, theta 2 divided by 2 as an average value to figure out what this integral is, just so that I could actually do it. Okay, so doing that, I would get h2 over h1 star would be approximately equal to exponent of CD over H star minus CF over 2 by the average value, and that would be x2 minus x1 times UE at 2, UE at 1, raised to the power of h minus 1. And I'll use the average value there. Alright, so that's making that approximation so that I could actually work this thing out, because as we know, these things are going to be functions. H is changing, or could be changing as we change in x. But in this case, we can assume that all these things are constant, so that we could do this approximation, and that's why I write it's approximately equal to in that particular interval. All right, so let's examine the terms in here. examine the terms in this kinetic energy equation. So as dUE dx less than 0. So for adverse pressure gradients, so if I look at that equation, if I look at my equation for H, if this guy is negative, so it's adverse pressure gradients, then H star would be getting smaller and smaller. And for sufficiently fast decreases for sufficiently fast decreases in my velocity, so in my du, so in this term, so for sufficiently fast, so if that thing is really fast, then I could represent that as this dx being really small. So if it's really fast, if it's a really large change, then this term is really large. So if that term to be really large, I could represent it as this dx, or x2 minus x1 being something really small. Okay? So for that change to be sufficiently fast, I could represent x2, x1 as something small. So as the change tends to go really large, this guy tends to 0. Okay, so if this guy tends to 0, so x2 minus x1 tends to 0, then let me see what that does to my approximation here. So if x2 minus x1 tends to 0, so this term here is tending to 0. So if it's 0, then means that this entire thing is 0. So exponent to the 0th power, so that's just 1. Alright, so that means that this guy, exponent of all those terms in there, tends to 1. So then I could rewrite my approximation in this case, H2, so H star 2, H1 star as approximately equal to 1 times UE2 UE1 to the H minus 1 average. Alright, so for this case, we're saying just for the decrease, we're looking at, say, a 10% decrease. So 10% decrease means that UE, so let me write that over here. Okay, so for 10% decrease here, it's pretty much saying that UE2, UE1, that ratio is equal to 0.9. Alright, so for this particular case, what we're looking at, so that means H2 star, H1 star is approximately 0.19 times H1, H minus 1 average. All right. So we could plot what this thing looks like. So we could plot what this guy looks like. So if we were to plot what that thing looks like, H star, H, so you get something that looks like this. Right there. This value is 1.5. this value here turns out to be 4. So this is what happens at separation. So at h equal to 4, where we have separation, the corresponding h star value is 1.5. All right, so let's see what happens for, say, the case where we had laminar flow. Question?
We're plotting H star, or we're plotting the ratio, H star 2 over H star 1 in that plot.
Here we're plotting H star.
Okay.
Okay. So, all right, so, okay, so let's see what happens with, say, laminar flow and turbulent flow over, say, a flat plate. So for laminar flow over a flat plate, we have H1. In that case, it's about 2.6, so that's the gaseous case, so that's about 2.6, yeah. And the corresponding H1 star value is about 1.55. And for turbulent flow, this H value, so the H1, it's about 1.4. So the H star value, approximately 1.85. Oh, I think the problem that we have in here, this guy here is plotting H star against H based on what H and H star turns out to be. This is something separate. Okay. Okay. All right. So we have an idea what the laminar and turbulent values at H are going to be. So now that we know what this relationship is approximately equal to, we could see what the H value is at that second location and see what value it turns out to be. All right, so we could use this relationship to figure out what that H2 value is based on our H1 value. So for that little change, what is going to happen to H2? What numerically is it going to turn out to be? So let's do that. So H2, so for the laminar case, H2 star would be 0.9 times, and that's H minus 1, so that's 2.6 minus 1, so that's 31.6 times H1 star, so that's 0.84 times H1 star, and we know H1 star is 1.55, so that's approximately, so that's about 1.3. And so this is 1.3, so at that second location it's 1.3. So if we go back to the relationship between H star and H, so H star and H, so H star value of 1.3 actually is somewhere down there, which isn't on this curve, which represents the quote-unquote acceptable values that you could have. So that means that for this particular flow we have separation. Okay? So we would have flow separation for this case. Flow will separate. Since H star And for the turbulent case, H2 star turns out to be 0.9 times 1.4 minus 1, so that's 0.4 times H1 star, which is 1.85. So this turns out to be about 1.78. So for this case, 1.78. So let me just go back to my figure, 1.78. So that's somewhere up here. So in this case, for the turbulent case, there's no separation. So flow will not separate. Okay, so based on if we were looking at laminar turbulent flow in either one of these cases, you'd either have separation or not. And let's look at the value for theta. So how much is that boundary layer going to increase? So let's estimate theta. And we'll do it for the turbulent case first. Okay, so I'll have to go back to my equation for theta, do an approximate integration. You're approximately equal to minus H2 on 0.9. So that means theta 2 over theta 1 would be approximately equal to 1.43. So that is about a 0.43% increase, approximately. Okay, so however, if so that's the case where that thing is varying sufficiently quick. But if so, we represented sufficiently quick by really small delta x, so x2 minus x1. But if delta x is larger, so say it's large, then there's additional terms that we need to look at. So there will be additional contributions from that CF term, so that skin friction term. And for slower decelerations, so the term multiplying that delta x value, the term okay, so that's just going back to this guy and looking at the term that's multiplying that delta x value. And what it does is that it helps alleviate the adverse pressure effects. So it alleviates the effect of the pressure gradient. But at the same time, it still increases your theta value, it still increases your thickness, but adds to Okay, so the term that we're talking about is this term, this 2 CD over H star minus CF over 2. So as H increases, this term, that term up there, becomes more positive, and it drives H star to be bigger. And that alleviates the tendency to separate. And that's, say we're looking at our figure again that we had before. So looking at these two terms again. So we're looking at H values getting larger and larger, so this guy gets larger and larger. And that tends to take you away from that separation value H of 4. Okay, so if the pressure profile isn't increasing fast enough, if it's a really gradual change, it tends to not separate. So there's a certain limit as to how fast that pressure profile or that adverse pressure gradient is going to be to cause it to separate. Okay. All right. So let's go back and check on. So this is just looking at the turbulent region. Let's look at the laminar case. So let's go back to the laminar case for a second. Going back to the laminar case. So we had H star, we said was approximately equal to 1.3, okay, which wasn't a quote-unquote allowable value. So that 1.3 is down here, so it's not on that allowable, quote-unquote allowable curve. So let's see what happens in that case. Question?
When I calculate the theta 2 over theta 1, which equals 1.43,
Yeah.
what kind of H you use?
What kind of?
H you use.
The H value we're going to be using would be for our turbulent case. So that would be this H value here.
Okay.
Okay. All right. So this 1.3 is below the allowable, below the permitted value for H star. So what happens in reality? So in real life, what happens, since this is below H star, so in reality, the flow needs to adjust itself so that it's no longer in that range where this value isn't allowed. So in reality, the flow, it separates and moderates the UE value. So what it does is that it adjusts itself so that it's no longer in that range. So it adjusts itself, and it does that by adjusting the boundary layer edge velocity. Okay, so it adjusts itself by moderating this value. So UE would decrease in this case. Via And some people refer to it as a quote-unquote blockage. Or, if we want to say, a displacement effect. And it does that in such a way so that that H star value would tend to go back to being at least 1.5. Okay, so if I was to look at our boundary layer again, so for our problem, so we have our boundary layer development as usual. It's increasing. Okay, and of course this drawing is exaggerated. So this here would be delta star. So in this case here, this here is delta. Let me draw that a little further because I want to put the velocity profile in. So this here is delta 2. So a boundary layer at this point would separate, and you'd have some backflow. And then you'd have this guy. And so this is what would happen in this particular case. So the flow is going to adjust itself so that it's no longer violating that condition. All right, so let's just look at that a little more. So, okay, let's consider a slightly different viewpoint. Okay, so let's look at the H, so that shape parameter equation, kinetic energy shape parameter equation, Hx 1 over dH star dH times 1 over theta 2CD over H star minus CF over 2 plus H minus 1 over UE du dx. Alright, so let's look at what's happening as we approach separation. So looking at this as we go in towards separation point. With our edge condition prescribed, so we know what the edge velocity field is. Alright, so we know what H, CF, and CF star and stuff, how it behaves. Okay, so if I was to look at, so we know H, if we were to plot how H varies with X, this is H, this is X, so H increases, tends towards, and at separation H is 4. So that's going towards separation. CF, that's this guy. And we know what H, how H depends on H star. H star. So as H tends to fall, DH star, DH goes to 0, or should tend to 0. Therefore, DH, DX, so as that tends to infinity, these guys should tend to infinity. Okay, so we could see from the equation, so we can see that dH dx is finite when it's about to separate only if this guy, so as this guy tends to 0, and for this thing to stay finite, then this guy here would also have to tend to 0. All right? So for this thing to stay finite, it only happens if this guy, that term in brackets, star has to tend to 0. Minus h minus 1 over u e d u e dx. That should also go to 0. So that's separation. Separation. So, or we could say it as UE. So UE as a function of x would have to adjust itself such that, so it has to adjust itself such that these two guys should be equal. Alright, so one should be negative of the other. So h minus 1 over ue d ue dx should be equal to cf over 2 minus 2c d over h star 1 over theta. Okay, now multiply, let me put theta over here, multiply throughout by theta. Alright, so at separation, the shear stress of the wall is going to be 0. So this guy here at separation, this guy goes to 0. So if that guy goes to 0, then due dx has to be approximately equal to, and I'll throw everything else on the other side, minus 2cd over h star. And that is times ue over theta divided by h minus 1. Okay, so the new boundary layer in this case actually determines the edge condition there once we separate. Via, and I'll call it that, blockage mechanism. Or the displacement thickness mechanism. Alright, so that due dx actually depends on what's going on with this guy. So it actually depends on what's happening with that dissipation coefficient. It would tell you how that, how your pressure profile has to adjust itself. Alright, so in other words, so this implies that we require some type of, we'd call it interacting boundary layer theory. Interacting boundary layer theory for the displacement effect. For the displacement effect. And whenever I mention this, I just abbreviate it as interacting boundary layer theory. So when you see that in your notes, because I'm not gonna write interacting boundary layer theory every time. So when you see that in your notes, this is what it means. Right. So it requires that some type of theory to figure out that displacement effect to see how the boundary layer adjusts itself. So boundary layer theory, displacement effect for so that the boundary layer can modify that edge. So it modifies the edge velocity so that due dx reaches the acceptable limit or the admissible value or limit. Okay, so usually in practice, du e dx is usually quite small in the separated region. Okay, so if I say we're looking at flow over an airfoil, my boundary layer develops like this guy, and then say it separates somewhere down here. So this is my boundary layer edge, that's my boundary layer thickness. So this region, the edge velocity is based on what's imposed. But once we have separation, then it actually is affected. So that UE is actually imposed by the boundary layer. Because of the adjustments that have to happen for us to stay within acceptable limits. Okay, so if I was just to look at this area where that separation is occurring, so just looking at the trailing edge of that airfoil. So initially a profile is going to be as we expect. But once we get to the point of separation, so in here we're going to have circulation, use a different color. Okay, so eventually you're going to have flow separation and you're going to have these eddies being developed, so you're going to have areas of recirculation. And your profile is going to go slightly negative here. Alright, so in here, so this would be your boundary layer edge. And what you tend to see is that the pressure is pretty much constant on the edge. So that edge is also approximately constant. And here, this is recirculating flow. And the pressure is nearly constant there also. Okay, I just want to make a few notes before we end. When we talk about separation and those boundary layer equations, or the thin shear layer equations, and the thin shear layer context. So when there's a separation region, but it's pretty small or it's limited to only a certain part of what you're looking at, usually your boundary layer equations could still be applied and gives you good approximations. However, if your separation region turns out to be really large, then you have to do something else. All right, so if we say had this case where we had just separation just at the trailing edge of an airfoil, then we could still use our boundary layer equations to get a good approximation to what's happening. However, say you had separation at the leading edge, so there's separation over the entire airfoil, then in that case your boundary layer equations break down. You could no longer apply those to see what's happening with the physics in that particular situation. All right, so if I was looking at, say, a case where I had an airfoil and my separation was right at the trailing edge, so I have my recirculation zone right here. So the trailing edge, so TE, trailing edge. And in aerodynamics, we call that trailing edge stall. So when you have separation, they call it stall. So we still have conditions where, so this guy is on the order of about 0.1. and we could still apply our boundary layer equations. But say we had leading edge stall. So say we had our airfoil, and separation occurs right at the start. So we have separation here. So we have areas of recirculation. And we'd have our shedding. So we have separation occurring at the leading edge. Leading edge stall. And then our assumption that this guy has to be small, this is going to be on the order of 1. And then we can't apply. Okay, so if you had separation in a large enough region, or once the order becomes larger, then you could no longer apply your boundary layer equations to those, to actually apply them. All right, so I'll stop there for now. And on Thursday, we'll start talking about this, this interacting boundary layer effect thing a little more, so we can understand how the edge modifies itself when dealing with things like separation. All right, see you guys on Thursday.